Okay, so now I will begin my talk talking about today's lecture on boosting soil fertility with chemistry. So there are two parts that I'm trying to emphasize here. The first one is on the soil fertility, talking about the significance of soil, of this topic, of this subject to our daily lives. And why do I choose chemistry? That is because I am actually a trained chemist. I'm actually start my academic life as a chemist, and then slowly I transition into environmental science. So here I am. I can at least call myself confidently that I can talk a little bit about soil chemistry here. Okay, so I am coming from the Faculty of Applied Sciences, University Technology Mahara, Malaysia. Now, for those of you who haven't heard about this university, please Google UITM, and then there are more information you can get from there. Yeah. Anyway, let me continue with the next slide. Now, what you are looking at is the lecture outline, the sections that I'm going to go through one by one throughout this 1.5 hours of time given to me. And I'm going to talk about the topics that are listed right here. While there are two parts that I'm going to add in due to the significance of it on soil fertility, which are the soil pH and also some extra that I'm going to add in the conclusion part. The rest of it, I'm pretty sure that is part of your learning outcomes as listed in the course the course file, the course information that is shared by Dr. Ratna with me. So I'm going to touch about all these sections one by one. Okay. So to begin with, let me start with the introduction of soil fertility. Now, what you can see right here is an image, a poster that I have collected from um, an organization, an NGO from UN. So this diagram shows you that how a plants can grow well based on the distribution of the elements already present in the soil. So later on, I'm going to elaborate what are those elements, their categories, and also the quantities that they are needed. Now, to put things in perspective, fertility, in Malaysia, we call it subur, kesuburan. Whatever that makes a plant grows well, that counts as fertile. Now, in this case, what you can see in the diagram shows you exactly nutrients plays a big part. So how much of that nutrient that can be absorbed by the plants, that is crucial to determine the soil fertility. Okay. So as the first point right here, as we can see right here, the soil fertility is the ability of soil to supply adequate nutrients for healthy and productive plant growth. So it must reach the plants no matter how. Okay? Now, the concept of fertility also depends on another factor. Now, even though the soil have plenty of these nutrients, it doesn't matter if it is stays in the soil and cannot be absorbed by the plant. So here comes a key word here, bioavailability. Now, a bioavailability is defined as how much the plants can absorb these elements from the soil. Now, there are many factors that determines how much of elements can be absorbed by plants, which mainly governs by part of it, mainly it's due to the chemical process in the soil. Now, that is what we are here today. We are trying to understand how the few chemical process, the important ones, plays a role in determining the bioavailability of these soil nutrients and how do they translate into soil fertility. So to begin with, what are the nutrients? I believe yourself at this point, you must have learned the elements that are important for plant growth. Now, in this case, we often refer it to as essential element. Now, there are 16 of them. I know if you are aware, the earlier slides, the earlier poster mentioned more than that, 18, if not mistaken. But to put it into simpler perspective, there are 16 of them, and all 16 are categorized in this table. The basic ones are non-metals like carbon, hydrogen, oxygen, which can be absorbed by plants through the air, atmosphere, have carbon dioxide, H&O coming from water from the soil. Those at this moment, although they are the primary elements for the building blocks for the photosynthesis, but usually it doesn't count as part of the plant nutrient. Now, plant nutrient starts from the middle here, the middle column. The macro. Macro means macronutrient. What are the quantities that are needed? More than 50 milligram. So as if you compare to the micronutrients on the right-hand side of this table, the last column, the quantity required is much lesser than that, less than 1 milligram per kg. So you might have used like other units like parts per million. So milligram per kilogram is equivalent to parts per million. So 50 parts per million versus 1 parts per million. That is the difference between macro and micronutrients in terms of the required quantity by plants. Now, another thing, one thing that I always ask my students to always remember, the examples of macronutrients and also micronutrients. I'm not sure whether that is your requirement, but it's definitely one requirement by my students. They have to know what are the macronutrients, which are pretty common and easy to memorize. They are, for some, NPK. And in fact, N means nitrogen, P phosphorus, K is potassium or kalium, sometimes you call it. Those are the three elements that are usually shown on the labels of your fertilizer. The chemical fertilizers or organic fertilizers, their grading, their quality is determined by how much of NPK is in the fertilizer. Yeah. So there are other secondary macronutrients such as sulfur, calcium, and magnesium. They're equally important, but for some reason it is not displayed on the page of the on the labels of the fertilizer. But you got the idea. There are 6 macronutrients, and the rest of it, 8 of them, right here, they are micronutrients. So you must have asking me, if you know carefully, if you look at these elements, some of them might be categorized as heavy metal. You are not wrong. You are correct. Like for example, zinc and also copper, they sometimes are called heavy metal because they also may possess toxic effect, but that depends on the quantity. And it comes down to this number. If the quantity exceeds 1 ppm or 1 milligram per kg, then they might be causing some toxicity to the plants. Yep. So this is the periodic table where you can see the distribution of the essential elements, the beneficial elements that you can refer to later on. So I stop right here and I move on to the next slide. Now, I know perhaps you have seen this before. These are the very basic information talking about the components in the soil, where it consists of atmosphere, the gases right here, the air, I would call it. And then after that, the moisture, which is hydrosphere, the water, the living organism, and finally the mineral phase. So all of which comes down to this distribution right here. So I'm sure you can see the mineral phase, the water phase, the air, the organic matter, and the distribution. Now, why am I stopping right here? That is the essence, the material that we're talking about. What is in the soil? Primarily, we're going to talk about minerals, the sand, silt, and clay, the minerals. Yeah? And the other part that matters a lot to the soil fertility is, in fact, the organic matter right here at the bottom. So here, the organic matter actually plays a big part. Now, this is the early information for you. Before I go to the details, you are going to expect that I'm going to talk a lot on how organic matter can contribute to the fertility after they undergoes a series of chemical process. Okay. However, this process cannot cannot happen without water. And as we know, water makes the cations move, and when the cations can come close enough, then only you have the chemical reaction. So what I can say is that all these components already in the soil plays a big part in the chemical process, in which they are quite complex, which I will explain later on. So this diagram shows you from left to right how the nutrients are released and gets absorbed by the root plants later on. So it begins with two components. On top of here, which is the organics, or at least it looks to me like the residue, the leaves or the twigs from a plant. So that is quite common. You look at any soil surface, that matter from the trees, they are very common. We call it organic matter. Now, moving on at the bottom, rocks, spheres that you can see right here. These represent the rocks and the minerals. Okay. So in nature, we have a natural process we call weathering. Okay. And this weathering process is helped by our climate. Like I'm pretty sure in Malaysia and also Indonesia, we share the same climate, which is warm, tropical environment with high rainfall. And speaking of which, the rainfall causes a lot of weathering. It breaks down the rocks into smaller particles, releasing the clay particles that contains maybe the elements that are essential for plant growth. And not to forget, the organic matters also may contains elements that can be used later on as nutrients by the plants later. So they breaks down into smaller particles, as you can see right here. So these layers that stacks together are in fact the clay particles. Later, I will show you the microscopic images of the clay that looks exactly like this one. And the organic matter containing functional groups, various of which I will explain later. And these small spheres, as you can see, these are the elements, the nutrients that are essential for the plants and gives soil the fertility it has. And eventually it is absorbed by plants. So in the middle here, there are water. Now, this is the generalization of the process that I'm going to repeat over and over again. I'm going to start with the mineral, which is the blocky phase right here. And after that, I'm going to move on to the organic phase, which is on top. So this is how the nutrients already present in the soil, either in the organic matter phase or maybe in the mineral phase, gets break down naturally and slowly releasing the essential elements that can be absorbed by plants. And of course, before they reaches this plant root, there are water. So all of which already in the soil. So there are uh, four forms of the nutrient source. Okay. And as you can see right here, there are four, starting with the soil mineral, then organic matter, as I mentioned earlier, and the liberated forms of this material, which are the absorbed nutrients. Now, these nutrients, you can imagine that they are also elements in the cationic form that are attached to the surface of either the soil mineral or maybe the organic matter. Whereas the dissolved ion still cations, but dissolve in soil solution, in soil water. So I probably won't going to elaborate too much given the time limit that I have. So I'm going to move on to the next slide and show you the process. So these are the many chemical and also physical process that explains how the nutrients, the elements, the essential elements are released from the soil minerals or the soil organic matter into the soil solution and also gets absorbed later on. So um, what you can see right here, there are five major processes that I would usually ask my student to get to know, beginning with the fixation process. So in this case, fixation is hold on. Okay, the fixation process is where available nutrients, particularly phosphorus, reacts with minerals to become chemically locked and unavailable. You might be asking why fixation is part of this discussion. Now, what I try to tell you that let's look at soil mineral right here and also soil solution. So, like I said earlier, soil mineral is the source of elements and also the nutrients. So everything is here. So when it wants to release those elements, it will have to be weathered. So in this process, it's called solution, and those elements will become soluble form. So they dissolve in this soil solution. Now, nature have a cycle of process. So even though I say that elements can be released from the rock to become a solution, there is a reverse of this process. Now, this process can be reversed in which the elements already dissolved in the soil can become locked back and they form the minerals again. Now, this process is called fixation. There are many more terms in chemistry that you can use. Either you can use precipitation, you can use crystallization, but in soil chemistry, we use the word fixation. Okay? So when does this happen? While the soil minerals can become soluble with more water, less water will reverse that. So solution in this process requires a lot of water to dissolve the nutrient, and for the nutrients to reverse back into the soil minerals, just take away the water. When it dries up, the minerals will becomes a soil mineral once again. Okay? So this process is in cycle, depends on how much of soil water is in the environment. Yeah? Okay, so this is the process, the cycle that defines the nutrients from soil minerals to soil solution. Now there's another source. Okay, there's another source of the nutrient, which is from the organic matter. Right? Now, like I said earlier, organic matter supplies ample quantity of potassium, maybe nitrogen, maybe phosphorus. So they are two a major source of nutrients, and their process is similar to the soil minerals earlier, but they have a different word. Yeah. Now, while the release of the nutrients earlier is called solution, the release of nutrients from soil organic matter is called mineralization, in which the definition mineralization is the process where soil biology breaks down organic matter to release nutrient into the soil solution. So I would like to repeat this word breakdown. Now, I know you are more of a biologist, and I think the word decaying and decomposition, microbial decomposition might be better off, yeah, to understand this thing. Yeah. So this process is caused by the uh, microbial action through enzymes, but this process still requires a lot of water. And conversely, it can be reversed. Now, the nutrients already in the soil can be reversed, and in this case, it's called immobilization. Now, the word immobilization means soil microbes ties up available nutrients into their own biomass and organic compound. Where these nutrients, once it is absorbed by plants, it is assimilated to become part of their structure, like it in cellulose, maybe in their muscle tissue. So you get the idea, yeah? Anyway, the last part that I'm going to cover, which is happening between the absorbed ions on the soil and also the soil solution. So these are the released cations there are interchange between the liquid phase in the soil solution and also the solid phase. Now, this process, which is the discussion on here, is called cation exchange. Okay? So it is a reversible process. So remember, yeah, it is not just one way. It can be reversed depending on where is the equilibrium. So the key word here is chemical equilibrium. If the chemical equilibrium shifted, then one way or another, the cation exchange will happen. Yeah. So it can move forward and it can move back depending on where is that chemical equilibrium. Now later on, I will explain. Yeah. So done with the first part. Now is the second part. I'm going to introduce to you the soil minerals. Now, in case if you don't know, soil minerals covers a large part of the soil science discussion. But in terms of fertility, I'm going to limit my discussion to just clay. And there's a very good reason for it. Yeah. Because what you can see right here is a schematic diagram showing to you how weathering process breaks down the rocks that we have. For information, Earth begins with rock, they don't begin with soil. Only with the prolonged weathering process that it breaks down into smaller rock particles and then further weather into sand grains, and eventually they become clay minerals. So clay is the so-called final product, the final product from the mineral weathering process. You must be asking me why clay is only focused here in terms of the soil fertility discussion. Now, there's one thing that you don't know is that clay, there are many types. Some clay, they are more fertile. Some clay, they are not. Which is why, I mean, it is quite common. Not all the soils that we have, not all the lands that we have are suitable for agriculture for this reason. Because the makeup, the parent material of this rock, once they breaks down into clay, determines how well they can absorb nutrient. Some clay can absorb more, some clay can absorb less. And there is a reason, which is what we are going to explain later. Now, I'm sure you have seen this triangle before because I remember that according to your schedule last week, you learned soil physical properties. And I'm pretty sure you're going to learn texture. So this is a triangle that you're looking at. And depending on the versions, there are clay right here, which consists the major part of the soil classification, soil texture classification. And when we look at the soil column right here, um, there are many horizons where the clay is mostly concentrated right here. And if this is the horizon that separates the B horizon is right here, this is where clay is concentrated. Okay, the BT horizon. When are you going to learn this? Next week, I believe. Yeah. So this is the general information that you need to know. Where is clay? Clay is not just available at the river banks or at the deltas where all the sediments are collected, but they're also very much everywhere within the land. Yeah. Okay. Now, so for those who don't know how does clay looks like, this is the schematic diagram. If we have a very high resolution camera or microscope that can zooms in into atomic level, this is what you're looking. This is what you're looking. Now, earlier I told you that some clays, they can absorb more nutrients, some clays are not. The reason is because of this. Because clay minerals, there are many types. But in general, they can be categorized into these two types of clay, which is the one layer versus the 2-1 layer stacking. Now, why 1-1? Let's look at here. Now, 1-1 layer is right here. So this is 1-1. What does it mean by 1-1? It means that these clay sheets consist of two layers. One is the aluminium sheet, yeah, and also the silica sheet. So that's why they call it 1-1. And if we look at the chemical structure, the structure of this alumina sheet, you can see that in the middle right here, this is aluminium. That is why they call it alumina sheet. Whereas at the bottom, similarly, a dark sphere, this is silicon. That's why we call it silica sheet. And if you remember, in terms of chemistry and their valency, silicon that has the same group with carbon would usually have four valency. Four valency means they connect to four oxygens, one on top and three at the bottom. So this is oxygen for your information, yeah? Okay, oxygen. It's quite hard to write using your mouse, so you can see this. So this is oxygen, and whereas aluminium on the alumina sheet is connected to six oxygen. So I know that most of you thought, how come alumina with the cationic charge of 3 plus can be connected to 6 oxygen? Now they have in chemistry we have a process called dimering in which alumina can form up to 6 bonds if they are formed in a series, yeah, in a series just like polymer, so they will be able to form this one. So that is the chemical topics, the chemistry that I will not going to explain. Now what is important here is that now that you know how they forms, the important part is, what about here? This is hydroxyl, and in which hydroxyl the functional group is OH. So this is oxygen, what's connected here is a hydrogen, which means that electronically, the surface here is neutral. So here is neutral, but at the bottom, this is pure oxygen, not connected to any hydrogen. So that's why it carries a negative charge at the bottom. Which is why when you look at the silica sheet right here, the negative charge at the bottom, and on top, they have hydroxyl. So that is why hydrogen bond can form if you have another one layer clay sheet stacks closely together, and that is why usually 1-to-1 layer stackings, they are very tightly stacked together and they don't open up. One good example of this type of clay is kaolin or white clay or china clay. These are the clay that when you even if you throw it into the water, they don't expand. They don't expand, they don't form the clayey water that you usually see after a heavy rainfall. Yeah. And they're usually used as a material for pottery. Yeah. Now, moving on, the other one, which is the 2-1 layer. Similar to what I've said, the only difference is they are looking like a sandwich. Yeah. In the middle is the alumina sheet, which is right here. And then on top and bottom, they are silica sheet. So silica sheet form right here, which means that the surface of this 2-1 layer are completely negative charge on top to the bottom. Now, why does this matter? So let's move on to the right-hand side. Let's say if these 2-1 layer sheet with a lot of negative charge on the surface, negative charge on the surface, and you have another 2-1 layer clay sheets at the bottom, similarly with a lot of negative charge on the surface, what do you think will happen when the negative charge comes close to another particle with a same negative charge? Logically, they will repel. They will repel and they will go as far as possible. Yeah, that is according to physics. Yeah. And with the lack of hydrogen bond, unlike 1-1 layer, they don't closely stack together. In fact, they are separated. So you must be asking me, then how come the 2-1 clay exists as it is? Now, not that you know, actually, in between here, there are cations. In order for these 2-1 clay to come together, there must be cations in between. So these cations may be 2 plus charge, or maybe 3 plus charge, because this one serves as an intermediate. When you have 2 plus charge, it neutralizes the charge on top as well as the bottom that allows these two clay particles to come together. Yeah. So what does it mean? Let's not forget, this cation is also possibly nutrient. So I think you possibly can guess which kind of clay minerals that gives a fertile soil. And the answer is definitely 2,1 clay. Yeah. Because why? They have a lot of negative charge. They can trap a lot of cations, and these cations are most likely nutrients. Yeah. So moving on. I promise you to show you the microscopic images of kaolin, the 1,1 layer clay. So this is 1,1. And exactly what the image earlier shows. These are clay particles. These are not papers, yeah, for your information. These are kaolin clay that they are stacked so closely together because in between these layers, there are a lot of hydrogen bond. They are very difficult to be separated, even with water. Whereas on the other side is smectite. Now, smectite is a different form. I believe smectite is 2,1 layer. I would need to confirm it on. Yeah. But next image will show you why we call 2,1 layer stacking clay also as the swelling clay. Because compared to kaolin that doesn't swell, 2,1 layer clay stackings, they can readily absorb moisture. And this is what we usually see, isn't it? After a heavy rainfall, usually these are the common clay particles in our soil. For a good reason, this will be the one that increase the fertility. At least when we talk about clay, when we talk about clay minerals, yeah. So once they absorb, they retain moisture. Remember earlier why water is so important? Yeah, they retain moisture to allow the chemical process to happen apart from the photosynthesis. And when they dry, you see the air pockets that they leave behind. So these are the air pockets that allows organisms to go in, roots to expand, and these are the natural process that allows the clay to retain not only nutrients, not only water, but also living organism because they also gives air. So there you go. Why clay are so important? Like I said, in between these clay particles, they are exchangeable cation. I forgot to add one important word. Not only cations, but exchangeable cation. Why? Because some cations, even though they exist, also sometimes quite difficult to come out because they are very strongly charged and they bind these two clays together very strongly. Talking about iron 3 plus or aluminium 3 plus. But the exchangeable cations that I'm talking about here, like lithium, sodium, potassium, maybe calcium, these are the exchangeable cations, also plant nutrients. So you can say clay is the parking lot. They are the sponge. They are the storage of the nutrients. Yeah? So I think that sums up what I want to say about clay. So you can say that the more clay that you have, the more fertile your soil should be. But is it true? I would say not really. Because why? Usually when the clay, when the soil have too much clay, they are too wet. Like for example, your rice field. Yes, rice field retains a lot of water. They can plant paddy. Other plants, maybe not. However, if a soil have a lot of organic matter, you can plant almost everything because soil organic matter works even better than clay. So here is how. Why soil organic matter is so important here is that it is the pool of nutrient, or rather call it a source of nutrient. What kind of nutrient that comes from organic matter? Majority of them, if it comes from plant, majority is potassium. If not potassium, calcium. and maybe a little bit of nitrogen. So these are the three major nutrients coming from this soil organic matter. Yeah. And then it is also the component of organoclayy complex. Why this is important? Like I told you earlier, clay alone is not enough to ensure a soil fertility. It must have the combination with organic matter forming this so-called organoclayy complex to really boost the soil fertility. Now, later I will explain later. And of course, it is a pool of carbon for source of carbon to allow soil bacteria to work. And for information, soil bacteria, like the ones that fix nitrogen from the air, that also gives a good nutrition to the soil. And also, it is the pool of energy. So at the bottom of these three, at the bottom of here, I will not going to touch so much because this is part of the soil biology, which requires another 1 or 2 hours to explain. So I'm going to focus more on the top two. And during the conclusion, I'll possibly going to touch about this one, the pool of carbon. So here's what you can see. Now, how does organic matter looks like in real life? You can be as green as this green material, the fresh residue we call it. And after a certain time, bacteria will decompose it, not bacteria, maybe most likely yeast or fungus, decompose it into dry leaves. And then one source that I forgot is animal manure. Animal manure is the feces of animals, sometimes human also count, although we usually use animal manure for boosting crop fertility, not we avoid using human feces. All of which they are organic matter. And after a complete decomposition, half composed, it turns dark. So usually the very telltale sign of the presence of organic matter in the soil is that the soil would usually looks dark, just like this one. And then when it fully decomposes, it looks very similar, only broken down into soil. It looks like soil because it looks so small, but 90% of this material is still uh, organic matter, carbon. Yeah. We have a name for this one, uh, which I will introduce you later. And you can actually plant anything by using this organic method, decomposed version. But if you have only the soil mineral clay, this looks very much like clay. You might face some difficulty in planting things. Nothing will grow well from here. I didn't say that it don't grow. It may grow, but it don't grow well. But if you have this dark soil, yeah, actually we have another name, which I'll tell you later on. This dark soil literally can plant anything. Yeah. So here we go. We are here on the next slide talking about the components of organic matter. So like I've shown you earlier, living organism consists of less than 5%, fresh residue less than 10%, and in which majority of the organic matter in the soil, they are either the decomposing version or the stabilized ones, in which each of them can range from 33% to 50%, which is good. The more the better actually. Now why? Why? Because eventually I'm going to go straight to the important part, which is, okay, I'm trying to find my cursor. Okay. The decomposing matter, which composes of 50%, happens to be right here as well. So why does this matter? Because all this while the process is happening, only this one sticks and remains. Humus is called a decomposed organic matter. It is more resistant, it remains longer. So in terms of the functionality and also the fertility of soil, most likely it is determined by humus because they stays longer. Yeah. Now let's say that the decomposing organic matter doesn't matter. It still does. It releases nutrient, but these nutrient when they release in large quantity, it doesn't stay. Then that is a problem because we want the nutrient to be absorbed slowly by the plants. But you see, plants are not something that works very fast. They work very slowly. So humus is still better, yeah, because they release the nutrient very slowly and it matches, yeah, the absorption rate of the plants. So what is humus? I believe you must have heard it before. Humus, aka compost, although I don't see it as a same. Compost is a bulk material. Humus is just part of it. Now, why humus is important here is that the shape of it. It is irregular. Now, compared to the clay particles where it is very segmented, very tightly arranged, very symmetry, humus is very amorphous. It doesn't have a fixed shape, but it does have an overall round shape. Now, why this is important? You can imagine that this humus particle as a spongy material. They have hairy materials that are very spongy, have a lot of holes inside there. And this is good because they are flexible, they are porous, flexible and porous, that they can merge well with clay. Now, clay is sticky and plastic. They swell and shrink. Whereas humus, they can swell, but they don't shrink to very small size. They will retain their porous structure. And this is good. Because why? When they have a porous structure, then they will have the ability to absorb a lot of water. Water is important for biological process, photosynthesis, and also the chemical process. But the chemical process, the chemical properties of this humus lies on the structure. So here you go. Very complex, a lot of hexagon ring, a lot of benzene ring. But the important part is right here. So look at here. This is even more important because while you can look at this entire dark structure as the body of the humus, the surface is what's matter, which is right here. What I'm trying to say to you is that the surface of humus or organic matter is packed and rich with negative charge. And this negative charge, they are carboxyl group, the phenolic group, and the alcoholic hydroxyl group. So these negative charge are very similar to the clay, except that they are flexible. There are plenty of it. And the wonderful thing about this functional group is that they can change. They can change over time. They can decompose by microbial activity and release nutrient. So once the nutrient is released, they also can absorb back into the humus itself through this negative charge, and also this negative charge. So it looks very similar like clay, except that humus is also the source of nutrient. So as you can see right here, the properties of humus, why they are so important. And in Malaysia, we have a subject that teaches students on how to plant things. And number one thing they're going to add in, I still remember, 30% of that mixture with the mineral phase is humus for very obvious reason. Because with humus, not only they are the source of nutrient, slow release. They slowly release the nutrients so that you don't need to keep on applying fertilizer. Humus is a source of nutrient that slowly release it, and humus itself traps nutrient. So even though the humus doesn't have enough nutrient, you put in fertilizer, they help grab the nutrients from the fertilizer from uh, being lost through leaching. Yeah, because when you give water, if you have excess nutrient, not trapped by anything, they just follow the direction of water in solution and they are lost forever. Humus will trap it. Yeah. And of course, there's one thing that I will not touch, which is humus is actually the habitat of the microbes. When you have microbes, you're going to be able to release the nutrient. And these are the things that unfortunately I will not touch in my lecture. Yeah. So okay. Now, moving on, soil water. So we have covered soil mineral. We have covered the organic part. Now the soil water. I think I've mentioned to you earlier that soil water is the medium to allow the chemical reaction to happen, which it is. But I would like you to see the structure of this water. It has a V shape, or we call it a bend shape. The reason why it have a V shape is because of this so-called lone pair electron. So this lone pair electron exists there. They pushes the bond. So that's why you have a V shape. And also, due to this existence of this lone pair, it also causes the water to be very polarized, in which at the hydrogen, it's literally a naked hydrogen, which is a proton. So this is a positive charge right here, represented by this delta plus, whereas electron, they are very negative charge. So they have a polar part on the top near the lone pair electron, and the positive charge part, which is at the bottom near the hydrogen. Why this is so important? It gives the unique properties of this water so that it remains liquid even with the extreme temperature. And not to mention that water is also good in buffering the temperature. It gives us a suitable range of temperature which the plants can grow well. Photosynthesis, obviously, and also the solvent of food and nutrients, where all the chemical processes are happening. And with this presence of water in the soil, it gives the special properties of the soil, aggregation, porosity, color, and whatnot. The one that I'm going to cover later on is this one, the exchange capacity. Dr. Ratna, may I know how much time left?
Oh, it's maybe it's 20 minutes. You still have
Okay.
time, 20 minutes.
Okay, I think I'm going to go really fast by showing you that, okay, so this is water. It may exist as a liquid, it may exist as solid. So on the right-hand side is the structure of water as a form of ice. Now, that is not what I want to stay too long with. Just want to let you know how water connects through hydrogen bond. So remember, the word here is hydrogen bond. They connect to each other. So what you can see right here is if you can look at the soil particles and also the water molecules together, they interact very differently. So what you can see right here, the darker sphere that surrounds the soil particles, they are called the adhesion water. So the adhesion water are the ones that are also called hygroscopic water. Now, this water sticks to the surface of the soil particle very strongly, and they are tough to release. Usually, these are the waters that stays with the soil, and the plants won't be able to absorb, but the microbes can, not the plants. Now, which part of the water that the plants can absorb? It's here, capillary water, or also we call it cohesion water. Now, these water are trapped in between the relatively bigger pores compared to the surface, like the mesopores, not micropores, yeah. These capillary water exists in the mesopore, and they are trapped there due to the capillary forces. Now, these capillary forces does not limit the water there. It still allows them movement. That it depends on the capillary force inside the soil. Yeah. Now there are many forces that dictates the movement of this water, which I did not cover, but generally these are the waters that you have. Oh, by the way, the last one, the air or the gravitation water. Now the name says itself, these are the waters that trap inside the soil, but they moves with gravity. Why? Because the pores are big enough that allows the gravity force to interact. So whether or not that water counts as a capillary water, a gravitational water, actually depends on how small the pores in between this soil particle. Yeah. So I have a question right here. Which type of water contributes to the soil's water holding capacity? Not sure whether you have learned this earlier in soil physics. Now, water holding capacity is quite important because that one, although it does not mention or dictates the soil fertility, but for the overall health of the plant growth, having optimal water holding capacity is extremely important because without it, the plants will die straight away due to the lack of water. Yeah. Now, to answer this question, the answer is all the water except hygroscopic water. Yeah. Uh, um, all the water except the gravitational water. My mistake. Because gravitational water, usually they are gone in a split second after gravity. The one that sticks in the soil particle are either hygroscopic water and capillary water. So when you dries it up, it counts as the water holding capacity. Anyway, let's move on. So this is how it looks like. The condition of the soil and also the content of water. When the soil have the most water, it has all types of water, hygroscopic, capillary, and gravitational. So literally all the pores, all the rooms inside the soil particles, they are filled with water. And at this state, we call it saturation. Saturation means they're full with water. Now, after a certain period of time, when the gravity pulls away all the gravitational water, you will have only capillary and also capillary and also hygroscopic water. So in this case, it is between the field capacity and also wilting point. Now, where is the wilting point? Wilting point is where the soil have no bioavailable water. That means the soil have nothing to be absorbed by the plants, have no water at all. That's why they wilt. Wilt means they sag and lose all the turgor pressure, so they sag. So this is where it starts wilting, and usually it doesn't come back. Usually when plants are wilting, then they die straight away. Okay, we're still talking about water. Now, next is cation exchange. I think this is the last part, and I have 10-20 minutes. I think I can cover everything. Anyway, cation exchange capacity is the major part in soil fertility. So to begin with, cation exchange capacity, also known as CEC, is the ability of the soil to hold nutrient. Now, it is a measure of how much of negative charge on the soil in general. Now, I mentioned soil. I did not say soil clay. I did not say soil organic matter. They are both. So overall, how much of negative charge in that soil? The higher, the better. That is because the more negative charge that a soil has, the more nutrient that they can restore, they can store inside. Now, in terms of mathematics, how do we determine that? We have a method we call sodium acetate method. Now, this is the experiment that I usually ask my students to do due to simplicity. We replace the surface with sodium, and then we leach the sodium and determine how much of sodium that we manage to replace. So based on the number of sodium, we also can translate to the equal number of negative charge, because logically, one negative charge traps one sodium cation, which is also one plus charge. And that comes down to this calculation. So in SI unit, we usually use centimole per kg. So this is the SI unit. The most easy to determine is, like I said, the sodium acetate method. However, for agronomists, people from the agricultural side or from the biology side, they would use this unit, but they are the same. They are interchangeable. 1 milli equivalent per 100 grams equals to 1 centimole per kg. Yeah. This is what I use, because as environmentalists, we always use this one. But for agriculture, that one, no problem. Now, this lecture will not going to cover mathematical calculations, so I think I'll leave to the existing team to cover on that one. Hopefully, their experiment to cover that. Now, this is the important part. What do we do? What can we do to increase cation exchange capacity? Now, before I read you the points, I believe you can read those points. I want you to look at this table. There are two tables, the top and the bottom. Where is humus? The very top of this table with the highest CEC value. So that is why when we have an infertile soil, a barren soil that we want to revive, that's very simple. You just pour as much as possible the compost, the organic matter. The humus already in the organic matter will help revive the CEC and increase their capacity to absorb nutrient. Okay, now I know that vermiculite, montmorillonite, and can also boost the CEC of the soil. We usually don't do that for one very obvious reason. Cost. Humus coming from compost, they are very cheap. You can make it yourself. Whereas vermiculite, montmorillonite, they can be bought from companies, from nurseries, but they cost a lot more than humus, which is why uh, commercially or logically, we always add humus. And although we can add vermiculite and montmorillonite, we don't do that because it's more expensive. Now, moving on to the next part. the bottom. There are different textures that also give you a different CEC value. Now we know that the loam clay texture, the clay loam texture is best for increasing CEC. But if you compare to this different texture, they don't differ that much. So that is why I still remember when my teacher asked me to mix humus and whatnot, they asked me, is the soil loamy? As long as it have loamy properties, it is good to go. Yeah. Just don't make it sandy. If it's sandy, then you probably need to add some more humus inside that. Yeah. So now coming back to these 4 points, what can we do to increase the CEC in the soil? Number one is definitely add more soil organic content, aka compost, or scientifically humus. Add more of that. Number two, although we can add more clay content, but usually we'll be happy with humus because humus is cheaper. Yeah. And then I think number three is nothing that we can do because the content of swelling clay is very much already determined. You choose one plot due to the nature of the parent material. The soil is already known to be either suitable for agriculture or not. So, of course, the type of clay. And then finally, the one topic that is not listed in the list of the intended learning, but also extremely important for soil fertility, if not the most important, is the soil pH. And in this case, in order to increase CEC, we will have to increase the soil pH. I think I need to correct here. It's not high soil pH, sorry. Because we need to increase it to a certain point, but not too high. If it's too high, the soil will not be fertile as well. Yeah. So here's a caption that I need to add here, which is up to pH 7. 7 is max. Maximum is 7. And for information, 6.5 is best. At the pH 6.5, 6.5 is probably the universal pH suitable for any plant growth. Yeah. So there you go. CEC. This is the process that we usually see. What's inside here is a clay particle, or you can also imagine that as a organic matter, in which they have something in common, a lot of negative charge on the surface. So on this negative charge, you already can see that potassium, calcium, or maybe some hydrogen ions already inside here attached. So they are still in equilibrium. Excuse me. Now, whereas this wavy structure are the soil solution. Now, every clay particles naturally will going to be surrounded by liquid. So this is the soil solution. And how does this process happen? I want you to pay attention to the bottom part right here, in which the existing ammonium cation already attached to the clay micelle may comes out, and then one hydrogen can replace it. Now, this will not happen naturally unless there is a very high concentration of H plus. So what does that mean? If H plus is extremely high, that means the soil is extremely acidic, isn't it? Yeah. When you have high H plus, that means the soil is acidic. That tells you actually soil pH, if it's not optimum and touches near to the acidic side, the soil will lose the cation, also the nutrient, and the soil becomes not fertile. So that is why usually farmers, they will go to liming, they want to increase the pH, not going to the acidic side because of this reason. Because acidity reduce the fertility. And similar, if we want to make the soil fertile, this is the reverse process where potassium goes in and then hydrogen cation comes out. So this is literally, this process is literally the reverse process of the earlier ones. Yeah. So this is what we call cation exchange. It happens when there is a change of equilibrium. And in this process, the equilibrium is the changes of the H plus cation. So I believe you must have heard this principle. It's called Le Chatelier's principle, in which this principle is one of the topics in chemistry, general chemistry, where we talk about chemical equilibrium. So what plays a big part in the cation exchange process depends on this principle, or in other words, the chemical equilibrium. So what makes this chemical equilibrium changes? Earlier is due to the changes of pH. That gives a different level of H plus. But in this case, when you have a plant that keeps on, so this is a plant here, when this plant keep on absorbing calcium, magnesium, potassium, and whatnot, you are going to notice that there will be a low concentration. Okay. Whereas clay particles that are the storage of the nutrients, this is high concentration. And we all know that root keeps on absorbing these nutrients, so they suffer low concentration. And due to this one, according to Le Chatelier's principle, there will be a net shift of the equilibrium to the left, and then there will be a transfer, so that this cation will be released. Yeah. So this is how cation exchange happens. In terms of what happened right here, this is the slow release. Slow release of nutrients from the soil with a high CEC that contains a lot of cation, so that it can be slowly absorbed by the plants. And of course, in order to reverse this one, we add fertilizer. Okay, so this is how cation exchange happens. So now, I think this will be the last part before I conclude the soil pH. Now, why I want to add this one in? Now, if you want to know, actually, soil pH is almost the entire thing when we talk about soil chemistry. Majority of the chemical process that happens in the soil initiated by pH, facilitated by water. With water, then only we have pH. Now, why this is so important? Because at a low pH, usually nutrient will be released, but you don't want to release too much that there's no more nutrients in the soil. And at the same time, when the pH is very low, let's not forget in the soil, we also have uh, aluminium that may be toxic to the plants. So that also affects the plant growth, although it is not going to play a part in the soil fertility, but it kills the plant and makes them not productive. So I think I'm going to skip this and move on to this diagram. If you haven't seen this diagram before, this diagram shows you the thickness, different thickness of every elements right here. Some of them, majority of them, they are nutrients. But when we move on to this part, which is aluminium and whatnot, these are the, sorry, not manganese. Manganese is supposed to be Mn. I think there's a revision here. Mg is magnesium. Manganese is Mn. So this here, why it matter? Because like I said, aluminium is phytotoxic, toxic to plants. And sometimes iron, when there's too much, the plants also cannot survive. So the bottom three, iron, manganese, and aluminium. If you look at acidic region, see how thick they are. This is why plants can be poisoned when they are too acidic. And when we move up to look at nutrients, they are so thick. So that gives you an idea. If the soil is too acidic, not only the soil is toxic, the soil also have no nutrient. So that is why I said pH must be in this discussion because it really controls the fertility. Now, the question is, what pH is suitable? Like I told you earlier, 6.5. This is where you can see that most of the elements are relatively big enough, they are more available, and at the same time, the level of the so-called toxic elements like iron, aluminium, they are the smallest. So at pH 7, the soil will be fertile because it contains a lot of bioavailable nutrients and at the same time, non-bioavailable toxic elements. So it plays two parts right here. Yeah. So like I told you earlier, soil pH and phytotoxicity. I think I will skip this one because I've already explained it earlier and show you the real data. So this is the graph that I have collected from a research paper published by Professor Shamsuddin of UPM in 2016. They conducted a research on rice yield from a paddy soil that is considered acidic, acid sulfate soil. So you can see that the yield of this plot of this paddy comes down if the aluminium is increased. So that shows you that in acid sulfate soil, there would be a net increase of the aluminium in the root, and that causes it disrupt the ability of the plants to grow well. And most of the time, it also interrupts its ability to absorb phosphorus. For your information, when there's too much of aluminium in the plants, it disrupts its ability to absorb phosphorus, which is one of the macronutrient. Yeah. And then what do we do? Well, if acidic soil is a problem, then increase the pH. How do we do it? Use liming. Now, liming is a process where we put alkaline materials like, for example, limestone. Limestone is the cheapest. You can use basalt, and I believe Indonesia have a lot of basalt. It's a dark rock. They are alkaline that comes from volcanic areas. Yeah. And I think this is nothing new. I think Indonesia use a lot of basalt, whereas in Malaysia, we use a lot of limestone, dolomite, somewhere in Perlis, that contains magnesium. Both, I mean, all three of these, they are alkaline materials that can neutralize the soil. The only issue is that all three materials are not cheap as well. So that is the issue here. Now, liming process is good because it improves the fertility by improves the absorption of phosphorus. When the pH is increased, then it reduces the toxicity from aluminium and iron. And not just that, with an optimal pH, the microbes also can work better. Yeah. And of course, the the limestone or the alkaline materials over there, they are rich in calcium, and calcium also is a macronutrient. So not only they increase the pH, they themselves is also the fertilizer. So this is a result. I think this one is a separate research from also from Prof. Shamsuddin's team. This one from the earlier page, in which they use limestone, and they mix fertilizer together. So they mix fertilizer and lime to look at the growth yield of the rice from paddy field, also from acid sulfate soil. So in this case, not only they neutralize the soil, but they also have like a net increase of the rice yield due to the increasing presence of calcium. So that gives you an idea. Not only calcium, not only calcium increase the pH to optimal level, it also helps in the growth and also the yield of the rice. So I think I'm nearing to the end of my lecture. So I think this one, perhaps I will just go through really quickly, in which this diagram shows you how the cation exchange process happened on the clay particles. So when calcium comes in, it replaces the hydrogen cation, and then it neutralizes the soil. So this calcium, once they replace the hydronium, they will stay with the clay and slowly they release to the plants. Now, at the same time, the carbonate ions, they comes down and they react with the displaced hydrogen to form carbonic acid. So this is where you can see from the carbonate side, it will help retain the hydronium and control the pH. In a way, it raises the pH. And calcium, when it goes into the clay particles, it revitalizes, it nourish the clay particles to absorb more calcium as a form of a nutrient. And so this one is similar and happens to potassium as well. So I think I will skip. And I move on to the last part, which is the conclusion. Now, for the conclusion, we all know that fertility is not just depending on the nutrients, but also how well the soil can retain that nutrients. And here comes two major factors: high CEC, as high as possible, and optimal pH. So the pH cannot be too high, cannot be too low. If these two comes together, usually the soil will be very well off and very fertile. Now, here's the way forward, the future. Okay. Now, in this case, we all know that clay and organic matter, they are very important. The higher, the better. But one thing that we always neglect is that they don't operate separately. Clay and organic matter, they actually works together, in which they form clay humus complex. And this complex, they actually gives us a synergistic effect. That means when they work alone, they are okay, but when it comes together, they work even better. So this complex reaction demands another 1 more hour to explain more details. But here I just want to tell you is that Indonesian government realized this. And in fact, there are some pilot project in Sumatra that uses more resistant organic matter like biochar. Biochar is like a carbon. It's like charcoal. You can call it charcoal, but biochar is more porous than charcoal. Yeah. We add this biochar into paddy soil, and then it successfully reduce the requirement of using chemical fertilizer. So how good is that? Indonesian government actually documented this one in the pilot project. They managed to invest a certain sum for applying biochar, but they save even more by saving from having to use too much of chemical fertilizer. So this next slide is actually captured from one of the reputable journals, showing you these test results, uh, revitalizing acidic soil. Instead of using limestone, they're using biochar. So you can see the result. With more application, higher application of biochar, they managed to increase the yield. They increase the base saturation, they increase the pH, and they reduce the aluminium. So this has happened in Indonesia. How I wish this would happen in Malaysia, but you see, Indonesian government have the will to do it, and that is a good news to let you know. Yep. So with that, that is all from me. I have ended my presentation. So over back to you, Dr. Ratna.
Okay. Well, thank you, Dr. Yong, for such a detailed and insight presentation. Um, we will now move to the Q&A session. For those who already have a question, you may raise your hand and open your microphone or type your question in the chat box. You may also ask your question in Indonesia because Dr. Yong is fluent in Malay. That is correct, right,
Yes.
Dr. Yong?
Yes,
So
yes.
please. As we waiting for the question from audience, I will ask you, Dr. Yong. What kind of lime do usually farmer apply to their soils? Is dolomite or limestone in Malaysia?
Okay. I not really sure the numbers, but I do know that dolomite is certainly one material that is sold in the market. I
Mhm.
myself have the chance to test it previously. But in terms of cost, usually dolomite is not the first choice, but rather we use ground magnesium limestone. I thought dolomite and ground
Dolomite.
magnesium limestone is similar. But then again, the popular choice is obviously limestone, ground limestone, the
Mhm.
powder form.
Mhm.
They are a lot
Mhm.
cheaper than dolomite. So I believe the most applied liming material would be ground limestone. But I believe there are certain parties that can afford a more expensive and more stronger liming material. They might choose hydrated lime. So these are
Hydrated
the
line.
yeah
Oh,
yeah
okay.
these are the three possible
Mhm.
things. I'm not sure because I have no contact with the farmers, so this is only my guessing.
Okay. And remember your slide is when farmer use biochar, it's more effect cost effective than lime. Is that true? In the term of price?
Okay. Actually, biochar is much expensive. It is more expensive than limestone.
Ah, most expensive.
It is
I'm
more
wrong.
expensive. No, it is more
Mm-hmm.
expensive than limestone, but
Mm-hmm.
in practical,
Mm-hmm.
limestone application have to be repeated. So it
Oh.
is cheaper. It is cheaper, but you
Mm-hmm.
have to keep on applying limestone at the end of the planting stage season. Okay.
Oh, at the end.
Yeah.
So at
Usually
the
at the end.
beginning and the end.
Yeah, at the end of planting season, when they want to recondition the soil for the next season, usually farmers will pour in the limestone to revitalize the soil. Then only they
Mm-hmm.
restart the planting. However, for biochar, I assuming that there's no loss due to erosion or whatnot, you only need to apply once. Yeah, you only
Mm.
need to apply once, and the application rate usually is a bit higher than the application rate of limestone. You have to apply more biochar, but it stays there. Compared to
Mm.
limestone, you have to reapply, but biochar you apply once. So in terms of cost effectiveness, I think I will use the presentation made by there's one Department of Agriculture of Indonesia who come to UPM and presented. They managed to show data, the real data of their saving from using less chemical fertilizer with similar yield.
Mm.
So so I guess that the
Mm.
saving is not from buying the biochar and also the limestone, but rather the saving from buying the expensive chemical fertilizer.
Okay. Well, students, would anyone like to ask question? Kalau mau dalam bahasa Indonesia juga tidak apa-apa. Nanti Dokter Yong akan menjawab atau bisa kalau malu bisa di chat box. Jadi seperti yang slide Dokter Yong sampaikan, kalau kalian ingat ya di mata kuliah fisiologi tumbuhan, saya selalu menjelaskan tentang cation exchange capacity. Ya, jadi why soil with high cation exchange capacity are considered fertile soils because the surface of the soil particle have a negative muatan negatif, so they can uh, grab cation with a positive, ya, holding capacity, yeah, how soil ability to retain water. And you have to remember about the field capacity in soil. That's the importance of a pore space, ya, space di antara partikel tanah itu penting karena di situ tempat ada oksigen, di situ ada air yang bisa diserap oleh tumbuhan. Ya, jadi kalau kalian perhatikan apa yang Dokter Yong sampaikan itu sedikit-sedikit sudah kami ajarkan di plan fisiologi lecture. Ya. And Dr. Young, I want to ask you one more. Is it true that applying a lot of fertilizer to acidic soil is ineffective unless the soil pH is raised first?
The answer would be yes, to put it
Hmm.
simple.
Mhm.
But to explain it, uh, because fertilizer, when we apply, assuming this is chemical fertilizer, we were going to spike the the levels of the nutrient in a short time.
Hmm.
So in a
Mhm.
way, there might be two possibility. The soil cannot
Okay.
hold it. Okay. When the
Hmm.
soil cannot hold it, then the nutrient have to go somewhere. So
Hmm.
here is the issue. Now, given that
Hmm.
our tropical countries with high rainfall, when rain comes down,
Mhm.
the nutrient will be leached away. So the issue is eutrophication, as we know. Okay.
Yeah.
But during dry season, when there is not enough rainwater, this nutrient may stay and cause another problem, which is uh, saline soil. Yeah, this is one part of the soil chemistry that I did not touch as well because there are too much of dissolved salt. It causes saline soil. And if you're talking about urea that has high nitrogen in dry season, and when you have a lot of nitrogen in the soil, they will turn into greenhouse gas.
Ah, yeah.
Yeah, they
Mhm.
will turn into greenhouse gas. So to answer your question, what should a farmers do in order to maximize the impact of applying fertilizer is that first of all, make sure that the soil has the capacity to hold it. Okay? In a way that in order to have this capacity, usually um, for any farmers, they will lime it first, but there's another way. They can condition the soil by putting back they say putting back the organic matter from the earlier season. Like for example, for paddy plantation, they have
Mhm.
those rice straw. In Malaysia, we call it jerami padi.
Rice straw, ya,
Yeah, the
jerami
rice
sama
straw
di
and
Indonesia
rice
juga.
husk. Um, the farmers put it back into the paddy soil. So this is one way to increase the organic matter and also the cation exchange capacity. Then after that, they will lime it. Once they lime it,
Oke.
all those negative charge will become very they will be ready to accept whatever the nutrients that you put in.
Hmm.
So this there are steps. There are steps that we need to do. So yeah, to answer your question, yes, it it has to be revitalized before we add more fertilizer. It's not just we add more fertilizer because of the impact to the environment that it may have.
Oh, Dr. Yong, is one question in the chat box from Caroline. First of all, thank you for the material provided. I apologize. Open pit mining activities in eastern Indonesia have caused severe land degradation. So, how does the removal of topsoil from open pit mining impact the soil biota community and the soil's ability to recover naturally? So, please, uh, could you answer it, Dr. Yong?
Okay, to put it simple, what we discussed earlier, we're talking about topsoil. But when it goes to mining, if there excavation, like what Caroline has mentioned earlier, you literally remove the productive part of the soil, the topsoil. So no
Mm-hmm.
life is sustained there. I mean, it doesn't bother the mining operation, but it does bother the natural process of the soil to regenerate and to produce. So um, the impact, I think, is quite obvious. Now, how do we recover from that? Um, I'm sorry. Is the question asking me how to recover, how to repair the soil, or how to or to explain the impact? What was the question
I
earlier?
think Caroline is as how does the removal of topsoil
Mhm.
from open pit mining impact the soil biota?
Mhm. Yeah. So we're talking about the impact, yes.
Mm.
So usually mining, they were going to remove the topsoil, the overburden. So when the topsoil is lost, you lose the organic matter, you lose the
Mm.
living organism that recycle the nutrient. So the entire surface of the soil without the topsoil is barren. Barren means not fertile, cannot plant anything. Yeah. Because if the topsoil is removed, you're literally removing the O, the A, and the B horizon. We're looking
Horizon,
at the
yes.
deeper soil or the
Mm.
C, R, or maybe the bedrock section, which are usually minerals, rocks, and most possibly is also acidic. It's also acidic, given of the lack of the nutrient cover that can hold those nutrient. Um, So, I mean, that is quite obvious that the loss of fertility and also the engine that recycle the nutrient. So that is the biggest impact. May
Yeah,
I
I think
ask?
okay, okay.
May I ask? Is
Mm.
the mining process about nickel mining?
Nickel mining? What
Is
do
it
you mean?
nickel mining or gold mining? Because you mentioned
Oh,
East Indonesia.
yeah, it's in Eastern Indonesia. I'm not quite sure, but maybe it's nickel mining.
Yeah, okay,
Maybe.
because I mean, Indonesia is very rich in natural resources. You have lead, you have mercury, you have gold, you have
Yeah.
nickel, even rare earth as well. So,
Yes.
I'm just because I mean, these different elements and their mining, although generally they require open pit, that means removal of the entire forest surface. Some of them might not be. Um, but they would general have the loss of surface cover, which I already explained earlier.
I know this, Caroline, as this question as a biologist. In fact, you are a chemist. So, Caroline, maybe this topic will, we are delivering this topic about how the impact of mining in the soil condition is maybe it's 4 or 3 weeks later. So be patient. Okay. I think there are no further question. And since we are also approaching at the end of our scheduled time, I will close today's guest lecture sessions. Once again, thank you very much, Dr. Yong, for sharing your knowledge with us. Dr. Yong already shared the lecture materials, and I will upload it to our learning management system, and you all can use them. Thank you as well to, I think there's one of my former student uh, is joined today. And as the moderator, I apologize for any shortcomings during the session. And before we end, I would like to ask everyone to turn on your camera for a quick group photo, please. This is for our documentation. Come on. Oh, this two part. So, okay. Nggak ada yang ketiduran kan? Rugi sekali kalau ketiduran kalian tidak bisa menyimak kuliahnya Dr. Yong. Come on, come on. Hanifah, Della, Aulinka, Yumna, Ananda, Tabina, who else? Sandia, Cecilia, Ibu Wahyu, apa kabar? Oke, I will count. 1, 2, 3. Give your smile. Wait a second. I will save it first. Wait, wait. On the second page. 1, 2, 3. Wait. Okay, everyone, thank you once again. Stay healthy and see you next time. And for everyone who is fasting, stay healthy and may your fasting go smoothly. Goodbye and wassalamualaikum warahmatullahi wabarakatuh. Thank you, Dr. Yong.
Thank you,
So
Dr.
we
Anna.
will meet 2 weeks again for
Yeah,
discussion okay. Thank you.
sure. Yeah.
Bye-bye.
Bye bye. Keep in touch.
Bye-bye. Bye.